So in chapter 14, exercise 11, it's asking you to predict the products for some reactions. And these are all acidic cleavage. So they're adding an excess halo acid, some heat, and an ether. So what you'd want to do is just draw a line down the oxygen of the ether, and really you can copy the rest of the molecule, and instead of the oxygen, you can put whatever halogen is there. So this looks a little weird. Let me just look at how many carbons I have. There's 4 here, so let me redraw that. 1, 2, 3, 4. We have an iodine coming off of the first one, iodine coming off of the last one. So these are really the same thing, but this would be a more conventional way of drawing this. And how you do this, how this happens, that's explained in the video for A, for 1411. But the process that we came to was to draw a line down the oxygen, replace the oxygen on both sides of the line with whatever halogen they're adding, and just make sure you add water. The oxygen in the water is the oxygen in the ether. The 2 hydrogens in the water are the 2 hydrogens that were with iodine in the acid. And that would be the product for there, or those would be the products for that one. C is interesting because we have to remember that one exception. So we see the ether oxygen, draw a line down that, and repeat each of these, redraw what's on each of those sides. And what we would normally do is replace the oxygen with whatever halogen is in the acid, so bromine. But if you remember, there's one exception. If you have a benzene ring, keep it as an OH. And the reason for that is that we saw that the oxygen gets replaced by the halogen through a substitution reaction, either SN1 or SN2. And that is energetically unfavorable if the carbon is SN2 hybridized. Now, we'll talk about the conditions that, what type of reactions you can do if it's SN2 hybrid, or if it's sp2 hybridized, and how to make that a substitution reaction there happen, but it's part of a future chapter. So for right now, you would just want to remember as an exception that if you have a benzene ring as part of your ether, to just leave that as an alcohol. And so those would be your 2 products here. Notice you don't have the water because the oxygen stays on the benzene ring. So this one is kind of similar. Draw a line down the oxygen. We would replace this. Notice we have this benzene ring though. And so that means we're going to leave this OH here. And on the other side we have 1, 2, 3 carbons. So 1, 2, 3. And instead of the oxygen we're going to have the halogen, so that's the iodine there. Notice we don't have water because the oxygen stayed on the molecule. This one is a little interesting. So similar process. You draw a line down the oxygen, and you could redraw this and replace the oxygen with whatever halogen is in the acid. The one thing, though, to be careful of is that you actually get, well, first of all, this is drawn a little strange, but this chiral center right here actually becomes a racemic. It becomes racemic, and the reason for that is because when you do the reaction, and let me just draw this out. Okay, so that's our ether. What would happen here, as we saw before, the first thing that happens is the oxygen attacks the hydrogen of the acid, electrons go onto the halide, and that would give you, actually, let's do this, that would give you this. And the way that we drew the mechanism for part A of this problem, was as an SN2 mechanism, with the iodide that was left over attacking as a nucleophile, and the leaving group leaving at the same time. But on this left side, this carbon here is tertiary, and so it wouldn't happen at the same time. It wouldn't be an SN2 reaction, it would be an SN1. If you remember, an SN2 reaction needs space, and this is very crowded, this whole area, because it's a tertiary carbon. This is a tertiary carbon, so it's very crowded, so it's hard for the nucleophile to reach. So instead what happens is the leaving group leaves as the rate-limiting step, and actually what you're left with is a trigonal planar sp2 hybridized carbocation. That carbocation is flat. It's planar, trigonal planar. It has 3 bonds around it, no lone pairs, so it's flat. And that means that this iodine, which can now come in and swoop in and attack, can attack it from either side. And if it attacks it from the top, say, it could become R, in which case if it attacks from the bottom, it would become S. There's no real preference for where it should attack, and so you'll get a 50-50 mixture of both R and S. A 50-50 mixture is called a racemic mixture. So the one thing you'd want to remember with this one is that when you redraw this, you can replace the oxygen with that halogen. Just keep in mind that at the second center here, you would draw it with the bonds in line. So you could draw it, for example, with this coming out, this other one going away, or you could draw this with the methyl group going away and the other branch coming out. And the truth is, the answer is really both of these. So you could draw one, and you could write En. En stands for the enantiomer, that's what this bottom one is. But you would get both of those products because this leaving group would leave as an SN1 reaction because this carbon is tertiary, leaving you with a flat carbocation that the iodine can attack from both directions, giving you the two enantiomers there. So that's the one tricky thing about that one. Just keeping in mind that you could have the 2 enantiomers. And the tip-off that could happen is the fact that one of these, not only did you have a chiral center, and that the sign for that was that you had the stereochemistry, but one of the carbons bonded to the oxygen was tertiary. So if you have both of those things, just watch out. You probably have 2 enantiomers as your product. And last but not least, for F, you see the ether oxygen, draw a line down the center, draw the pieces on the left as one thing, but replace the oxygen with whatever the halogen is in the acid. Draw the carbons on the right as one thing, but replace the oxygen with whatever the halogen is in the acid, and then just add water. The oxygen in the water was the oxygen here, and the 2 H's were the H's that used to be bonded to the bromines. And so that's how you can predict products that you would get for acidic cleavage of a few ethers.